Hi, everybody. So I'm really excited about this session because this has been my passion for the last few years, this area of deep learning. And we're going to hear from some people who have been using it in some really exciting ways. Before we do that, let's have a little introduction to deep learning so we're all on the same wavelength. You might remember I talked in the introduction to machine learning section about the birth of machine learning 60 years ago. And this here is the father of machine learning, Arthur Samuels. And here he is playing checkers against a computer. And this computer, he did not program how to play checkers. Instead, he had it play against itself thousands of times and figure out for itself how to play. In fact, by 1962, this particular computer had beaten the Connecticut state champion. So machine learning, as we've talked about it as a field, has had a lot of successes, and particularly recently, it's impacted all of our lives. We also talked about how it has had some limited impacts in medicine, perhaps most famously the computational pathologist. And as we talked about, the computational pathologist has the classic signs of being a kind of traditional machine learning algorithm, which is these things like relationship of contiguous epithelial regions with underlying nuclear objects has to be developed as a feature. The idea of relationships between epithelial and stromal objects has to be developed as a feature. These kinds of systems required very large numbers of very smart people to get together, the domain experts to come up with the ideas about maybe these are the kinds of features that are going to turn out to be interesting, and then computer programmers to handwrite the code to actually create these features. The final step of actually putting all those features into a machine learning model was really the easy part. So these kinds of systems worked well, but they had a number of drawbacks, one of which was they were limited by the creativity and imagination and capabilities of the domain experts and computer programmers that built these features. And in the end, we were only able to model things where we had some ability to describe what we think that model ought to look like. In 2012, the New York Times had a front page article about something very different. And it was about this thing called deep learning. This is Jeff Hinton, who many people would call the father of deep learning. And he was actually featured in this article because him and his team had won a competition that I was running. And the competition was about automatic drug discovery, more specifically chemoinformatics. And Hinton's team, in 2 weeks, when it says no specific knowledge, what this actually means is nobody on that team had any background in life sciences to speak of. And in 2 weeks, they built a chemoinformatics algorithm for predicting the toxicity of drugs, which was more accurately than anything that anybody had come up with. And the sponsor of that competition, Merck, went on to, and I believe they're still working on commercializing that system. Also in this article, they showed Rick Rashid, who was then the head of Microsoft Research, demonstrating a real-time voice-to-voice translation system where he was speaking in English and Mandarin was coming out the other end. Now, this was back in 2012. As you might have noticed, nowadays when you open up Skype, this has now turned into a product. It will ask you if you want to use the automatic translation functionality built into the system. Now, the ability to generate the state-of-the-art chemoinformatics algorithm, or something that can translate spoken English into spoken Chinese, clearly goes far beyond the ability of knowing what to look for and manually coding features. The trick to these kinds of approaches was something that would automatically generate those features. That's really the heart of what deep learning does for us. So deep learning consists of 3 pieces that work together in a way which is unique in human history in terms of what it can do. The 3 pieces are an infinitely flexible function. So the particular function is something called a neural network. And a neural network is mathematically provably able to approximate to an arbitrary degree of accuracy any function you can think of. Now, when I say function, you might think like y equals ax plus b. But when I say function, I mean like the function that turns spoken English into spoken Mandarin. That's a function, it's just a really complex one. So when we talk about infinitely flexible, we mean it can do anything which you can imagine is doable with data. So if you have an infinitely flexible function, it probably has a lot of parameters. And indeed, these generally have a number of hundreds of millions of parameters. So we need somewhere to fit those parameters. And this is where something which our next speaker will talk about briefly, backpropagation, comes in. But we have an ability to take this infinitely flexible function, feed it with data describing what outcome we want, and it will learn to fit that function to that data. Now, these two pieces have existed for some years. The thing that only recently came along was the ability to do that in a way that is fast and scalable. In particular, we use the graphics cards that are used to run modern AAA video game titles. Those graphics cards have had billions and billions of dollars spent on them in order to get really good at creating spectacular water effects or gunfire effects or so forth. All of those effects, it turns out, are basically require you to be very good at linear algebra, multiplying a matrix by a matrix. And these pieces here happen to require almost exactly the same things as those computer games require. So it turned out that we could repurpose these graphics cards to get them to build and train these neural networks. So these three things are unique in human history because suddenly we now have something that can solve any problem for which we have data without anybody having to describe how to solve that problem, or even what are the kinds of features that would solve that problem. So this is being used very widely right now. For example, you can download from Microsoft for free a program that will take an attempt at creating a panorama like this, where you've cut a whole bunch off. And this is an actual real example where it has filled in what it thinks might have been missing. So for example, the entire right-hand edge got cut off, and the system noticed that there seems to be some cars here, and it's invented some cars. So when you hear, for example, people talk about, oh gosh, it's really hard to use machine learning in medicine because we have missing data, we have systems that you can download for free to create whole images. The idea that missing data is some problem we can't get over is definitely not the case anymore. Here's another great example. Here is somebody drawing a beautiful picture, and then they've decided to take this picture and say, please turn it into something in the style of the great Impressionists. And it has automatically created a painting. Now, neither of these programs were coded per se. All that happened was that they took that infinitely flexible function and gave them data that represented examples of, in one case, what the world looks like, and in another case, what Impressionist paintings look like, and it figured out how to do the rest. So, as I mentioned earlier, I kind of thought that this would be interesting to apply to medicine, and the obvious place to apply it would be in radiology, because radiology is very much imaging-based, and imaging was something that was already getting a lot of good results. And these are the results we found. When looking at malignancy prediction, we had much lower false negatives and much lower false positives with just 2 months of work, with a group of 4 people, none of whom had any background in medicine. And we're going to hear from one of our other speakers today who's going to be talking more about some of these opportunities in radiology, which are huge. It's important to understand that this is not a speculative technology that may or may not work on the kinds of things that doctors do every day. This is something that is now being very widely used. For example, Baidu, which is kind of China's Google, if you like, has a system which recognizes Mandarin Chinese and does speech recognition on that more accurately than native Chinese speakers do. The systems for image detection using deep learning are more accurate at recognizing the content of images than humans are. And interestingly, every one of these systems I'm talking about are not, they're not whole new algorithms for each one. This is just basically the same algorithm which is being retrained with different data. In one case with voice data, and the target is this is what the person said. Another case with artistic paintings. Another case with images. Or in another case, Go boards. So it's actually interesting to learn a little bit about how this worked. What happened here was that to win this Go game, this learnt, the same basic neural network learnt what does a good Go board look like. And so the same algorithm learnt to recognize good Go boards and therefore create them, as was used for everything else I've shown you so far. So to close, I really wanted to talk about how this is very likely to impact every part of medicine. You can see that because you look at Google. It has happened in Google that there's been this hockey stick growth of the number of projects using deep learning at Google. It's being used in every part of the business. And we're now up to thousands of projects. And Google only started using it in kind of mid to late 2012. So they were one of the first. So just imagine if your hospital started now, what are all of the areas that you could be impacting medicine in 3 or 4 years' time? And indeed, your growth will probably be faster because nowadays there are far more systems available for you to build on. So hopefully we'll learn a little bit more about some of these opportunities.
Thank you. So there was a session where they stood for the whole lecture. I think we'll lay down for this one. Now my frontal lobe tells me not to do that. I might kicked off the planning committee. Oh, beautiful. Okay, here. So my challenge was to try and help everyone understand the difference between sort of human cognition and machine learning and deep learning. I think some of the things that I was going to talk about were cognitive biases a little bit. We'll get into that as well, but Rachel did such a good job with that, and Wen did such a good job with that. We'll probably skip over that a little bit. But I think it's probably a good idea to maybe start with how the brain works in general. You know, I think a lot of times when we make comparisons to human cognition and machines, we skip right into adulthood. And that's not what happens. The brain is actually born with many, many, many more synapses than you need. And then there's a pruning process that gets undertaken. And we think that probably in cases of autism, for example, so Spiro's example of Rain Man is that he's very good at obtaining information, storing information, but not so good at processing it in a meaningful way. And so there's actually a developmental, so as a pediatric neurologist, we follow the brain in time. There's a developmental process that happens over time. And what we see is that as the child is exposed to things like the mother's face, right, being breastfed, right, you start making these connections. Well, this is my mom. This is who gives me nurturing, right? This is what my mother's scent is like. This is what my mother's face looks like. And then that impression gets embedded into those neurons, and those neurons get strengthened. And if you take a child and you leave them out with the wolves, they're never going to develop language. And it's a timing as well, right? So they won't learn the sounds, human sounds, and so they will not be able to develop language. And if you miss that window of opportunity and you pick up that feral child at, age 7 or 8, they're unlikely to be able to learn any language because they've missed that window of opportunity. And what happens is the arcuate fasciculus, which is the language bundle of fibers, gets repurposed for something else, maybe wolf speak. I don't know. So anyways, so that's just a quick primer on sort of how the brain develops. And I thought vision actually, because vision seems to be the hot topic, right? So how does Google see? How does how do all these AI algorithms, how do they see? And we're going to talk a little bit about that more. But the brain is sort of organized in this hierarchical pattern, which we talked about as well before. And it moves in these higher order up and down channels. But at certain levels in the cortex, there's also this across connection that happens. And we know that that's not so far off of what we were thinking back in 1948, right? So that's actually Turing's actual paper, right? And he described that neural network, right? So that we were taking some inspiration from neurology or neurosciences and saying, how do we leverage those? But I think there's a very different concept. Instead of taking and trying to just mimic or copy something, right? We can use that as an inspiration. We can use that as maybe even something that we have to be careful about copying, right? Anthony has a great example where he talks about when humans were trying to learn how to fly, right? What did we do? We threw on wings and we jumped off cliffs and we died, right? Because we thought we could flap our ways into flying, and we didn't realize that although we can be inspired by birds, the reality is that it's about aerodynamics. And so we don't need to copy the bird in order to fly. We need to understand the mechanics and understand how it works, and then maybe we design something totally different, and then that's what gets us to fly. So I think we need to take inspiration from the human brain, but I don't think we need to copy the human brain. So let's talk a little bit about how this works. So images come in, and you do have some rudimentary shapes that your eyes will pick up. So it looks at and it sees edges and shadows and light perception. And these things sort of keep going up into higher order things. So you have, let me go actually back one real quick. So what happens is that the vision comes in, and these are just basically long tracks, and they actually will go to your primary visual cortex. So when I talk about V1, that's your primary visual cortex. And basically that just sees shapes. And then those shapes actually get abstracted up into the secondary visual cortex. So now this curve, starts looking maybe like the letter C, but maybe it could also be part of the letter 8 or a G, right? And we're really good, and you've all seen those internet memes where they give you some bunch of letters and they're all jumbled up, and then you have to sort of figure out what that text is. So we can do that because we take in to V2 and we start saying, okay, anything that has this curve, it could be a C, it could be a 6, it could be a G. I'm starting to make some associations with it. And then once I figure out what that is it a face, an ear, an eyeball, then I start associating that to, well, that looks like Bill or Tom, and Tom's a male, and Bill's a male, and Fred's a male, right? And so I start clustering these ideas together, that these people have this associated concept with it. So there's this association concept mapping that happens, or that is in the brain. And we're good on 4 minutes. And so those higher level associations actually take place in the association cortex. But this is not in isolation, right? Because if I think about, my friend Jane, who's a female and who's nice, I'm actually also thinking, I'm raising to the surface that, Fred's also nice, right? And maybe Fred and Jill are dating, right? So all of these higher order concepts are coming together. Or if I think about my mother-in-law, she makes really good apple pie, and if I start thinking about that, I start thinking about the smell of apple pie, right? So these associations come together. So the visual cortex is now making connections to other parts of the brain. So this is actually a really cool project. Right? This was looking at numbers and having the machine recognize them. And in the true fashion of collaboration, I'm going to pull Jeremy up here, because we're not, I'm not going to pretend to be an expert on this. But so we have these are the numbers and the training set, but then you could do this kind of funky, weird bubbles, and the machine learning knows, okay, well, that's actually also very important, and that's a 2. And so we're going to go through this together. So Jeremy, you can come join me over here. So basically,
maybe just go back to the previous slide
sure.
first, because I think that's a really interesting one.
This one?
Yeah.
Yeah.
So interestingly, you can take one of these 50 or 100 layer neural networks we've talked about and actually visualize what each layer has learned. We don't tell them what to learn, but as Sharif will explain in a moment, we use backpropagation to figure out what's the best to learn. And when we go back and we look at the first layer of one of these neural networks, it turns out that they learn to find edges. And it turns out that the second layer learns to find simple shapes. And later on layers learn to find kind of parts of objects. we've also more recently built something called multimodal networks, which can jointly learn both language concepts and visual concepts. And it turns out that when we actually map the visual concepts to the language concepts, they actually appear in the same mathematical space. So really, what I hear Sharif talk about here in the brain sounds remarkably similar to what my neural networks teach themselves to do.
And so I think that that's actually an important point. So we took inspiration from biology, and biology is sort of mimicking what we took our inspiration. Now the machine learning is mimicking what we see in biology, and we've seen that actually too with evolutionary systems, right? So these concepts of causing evolution in your training modules or your training algorithms is the same as evolution that we see in animals as well. So, because we're trying to get deep into deep learning, you have an input layer, right? So you have this training set of images, and if you're good and you're aware of your biases, you'll make sure that you have the right ethnicities and genders and all of the things that you need, so you have a good data set. And then basically, like we were saying, it goes into some hidden layers. So you have this sort of shapes and edges and things like that, and then they sort of keep moving.
And just remember, these are not programmed.
Yes.
They get learnt automatically. The computer figures out this is the best, most efficient way to structure this.
And I think we're getting about 1 minute, so we'll do this. So I'll do this quickly. So if in the same way that we have a back propagation that happens in machine learning, the brain actually does this as well, right? So I have reinforcement. And so if one of my friends was telling me he taught his kid all the animal sounds wrong. So when the machine went, or when they let his kid hear a sound of meh, he told it, oh, that's what dog sounds like, right? So he actually trained his kid wrong, which is really messed up. But so he got all this reinforcement. Now the kid went to kindergarten, and he has to unlearn that stuff. So in a way, you have sort of this if you reinforce something wrong, you have to back propagate it as well in neurology.
Right, and so in a neural network in a computer, what we do is it goes through to the end. We then compare the output it guesses to the true output. We take the difference, and then we back propagate it through. And even as Sharif mentioned, we start off with something that is massively over-parameterized. And in order to ensure that we don't get Rain Man in our neural nets, we actually throw away half of the connections every time we backprop. So we're actually enforcing that it's never going to overlearn a concept.
Yeah, and then there's reweighting that happens as well. Just to quickly talk about this, so you have basically the filter, the threshold, the pool, and the normalization. This is sort of how you actually can either linearly or non-linearly look at the data before it kind of comes into the end output. Do you want to maybe briefly?
No, we probably should move on.
Going. Yep. Oh, yeah, we're time up. Okay, hang on 1 second. So I'll skip that. This is actually very interesting. So this is after you've trained the machine learning to look at images. You can go back to any one of those layers and say, show me something, create something new. And so this is the AI basically creating artwork, and the AI also is naming. They're using AI to name the artwork as well, and I thought these were interesting. And depending on where you go in the neural network, right, you'll get something, because this neuron in the neural network cares about trees and mountains. This one cares about, architecture of Asian inspiration.
Actually, something that just came out about 5 days ago, which is really extraordinary, was something where you basically take that approach, but you start out by you give it a sentence, and you basically say, imagine something that would match this sentence. And there's actually, I'd love to show you the results, but basically it generates photorealistic images that look like the sentence that's been described.
So I just wanted to put in a plug. I know we had shown a lot of fried chicken and labradoodles, but the human mind also has problems with certain visual tasks, right? So this is a really confusing image, right? It's real, it's there, but your brain has to go, what the heck is happening, right? Or, is this lady related to Aladdin, right? Is she on a flying carpet, or is that actually the shadow of a flag, right? So our mind actually also has problems. So I think it just repoints back to what we were talking about with biases, and I'm going to skip through these. But this is a great tweet from Melinda Gates. If we're going to create AI that works for all people, we need diverse people building it. So I'm going to go be one of those diverse people, hopefully. I think this was also a good example. I have a Ford Fusion, and my wife hates sync in there. And then we already talked a little bit about that. So thank you, guys.
Thank you, everyone. My name is Fabian Beckers, and I'm the CEO and co-founder of a company called Arcturus. And I just want to premise to say it's fantastic to be here and to be in a community building and always trying to advance a data-driven medicine, which is a true passion of mine. I think humanity needs it. So we created Arcturus 5 years ago with the exact goal of that. Today, if you see 5 different doctors, you have somehow the chance to get 5 different diagnoses. And I think the world needs to change that. I believe that's all what we're trying to aim doing here. So what we've seen in the latest trend at the moment, we've seen hospitals truly want to transform now their data into insight. We've seen pharma that want to make more personalized drugs. We've seen tech companies wanting to enter into healthcare, but sometimes they build models. Sometimes it's hard to transform them to clinical applications. And all the big OEM vendors are building platforms at the moment to try to connect their devices together. So there's a really exciting time where this dream that we have is about, I think, is happening really at the moment. One of the dream that we have and the vision we're trying to build is the following one. So we take a scan, it goes through the cloud, you have AI, deep learning, and probably in the future other algorithms as well that we can leverage to fully do an auto report. Having doctors 12 years trained doing contours and manual work for hours on end is not the best use of their time. And then what we're also now working into is to, once we have the diagnosis being done, we bring the text data. And I think deep learning is very good at finding similar cases to try to really bring the outcome data in a way to inform the diagnosis. And so that's what the journey we are on at the moment. And so one of the big problems that we faced when we started this journey 5 years ago is the following one. Hospitals today, in many places of the world, act as a bank or a jail. Their data is there on servers, sitting there taking dust. They have little CPUs, static software, and so therefore, with that structural environment, it's logical that physicians spend a lot of time considering how variable are medical images. That combination structurally cannot work. And so they spend a lot of time manually doing a lot of work that can be automated. And so the transformation we're trying to build is to go from that model to this one. Try to break the wall, to try to leverage unbound amount of computation and AI to bring those data and those physicians as input together. And so for that, we had to build for 5 years a whole new OS and pipeline to deploy those models. So we worked with GE heavily, and we launched a product last year and this year again to integrate deep down. Healthcare is fundamental, an industrial equation. If you don't take into account those vendors, it's very hard to scale. The second piece, what we had to deal with, is PHI data, patient health information. If you don't account for that, you can be Google, GE, IBM. The hospital will be very reluctant to send data, personalized data to the cloud. It's very hard to do on a large scale. So we had to deal with that. The other piece is that in the browser, in the cloud, you need to have a lot of compute at load balancing and GPUs to deal with a global approach. So we work in Europe, working in Patagonia, working in Sydney. How are you going to deal with that in a dynamic way? And then you have to have an interface and of course with AI, and also an interface which is very important. You use a browser as a means to look at the data. But what we are building through that interface is a way to create a one-to-one connection between the physician and the engine. And so every time a physician does something in our interface, we learn. And that's a very big paradigm shift on how healthcare is done today. Let the system get smarter over time. And we've seen a long tail in many other industries. How powerful is that approach? And so that's what we've done. And so as a result of that, we also wanted to do that in a very clinical fashion. So building a platform is great, but we want to solve a very important clinical need. So we started in cardiac when we felt it was a great beachhead to demonstrate that paradigm. And so today, that's the way most of physicians sometimes look at the heart, and they use an echo. The problem with that is the flow information you have on there that sometimes trigger open heart surgery or valve replacement is fully based on indication. You don't have quantification. You don't have precision. So you have babies that are born with heart defects. You have adults with valve. And literally, the surgery can be based on those information. So we create a new way of looking at MRI and switching the code to be able to have those kind of acquisition. So now we can see the heart in full anatomy and phase and flow in 10 minutes or so, free breathing. That takes an hour to an hour and a half today. You don't even have the same level of information. The problem we had with that when we started doing this is that the file size is extremely large. We're beyond 100 meg that the packs can handle. We have 4, 5, 10, 20 gigabyte data. So we had two ways. Either we install a supercomputer at each hospital, which is very hard, or we leverage the cloud, and that's what we've done. But that is only one half of the equation. The second part is that once you have the data, doctors literally spend hours drawing the left ventricle, the right ventricle in diastole and systole, and that can take 96 contours. And the last 20 years with signal intensity type software, none of them been solved. It's still a very manual process. And so with deep learning, this is what we've shown. This is fully applied, 100% computed with zero manual intervention. The system has learned to recognize that we've done that in weeks compared to 20 years on a local software. And every time the doctors will change, the contours will do and will propose, we learn. And that's the pipeline we created over, and then of course integrated with GE. And so as a result of that, with all those pieces, we have now really through that, and of course we have to deal with data privacy in different regions. We have to deal with FDA and CMARC. I mean, it's a lot of pieces to put together. But now we have a real platform, and then the beauty of what we're entering now is that for us to create a new application is extremely quick, in weeks, and I'll show you a few examples afterwards. So we just build models, we use ground truth, roughly 1,000 cases with ground truth and curated data is needed. We'll build a model, we inject it into the system, and weeks later we have an application that we can distribute it over the world that physicians can use, make modification and change, and then keep training the system. And so we've done that on many applications and many pieces. Now we're entering the world of oncology, which is extremely needed for this kind of approach. One of the part we did is to deal with PHI. So when we do a scan, the patient health information is taken out of the scan, remain in the hospitals, and it's only de-identified data that goes to the cloud. And then in browser, the two data are put together, and when the physician can search a patient name, it will go through our PHI service, but we never see the color of a patient name. And that's a very important piece of technology, is a clinch pin to truly enable scalability and quick adoption of the cloud in the healthcare space. Otherwise, in US especially, you have to go to a BAA, and security review takes months, and a startup is absolutely not doable. So it took 2 years to build this, and now it's going to be deployed over many, many hospitals. And so once you have done that with one hospital, like at Stanford, for example, that uses it, now you can start connecting hospitals. So we're uploading at the moment, with having launched in January, 200 gigabytes of data a week, and we're going to up to probably like multiply that by 10 in the next few months. And so now we're starting having like 6,000 cases. We have 40 hospitals, and physicians keep learning from each other. And I think that's really proven that in cardiac, which was so complicated, the power of that model. So we can truly leverage the data. And so now we're also building APIs to even accelerate that speed. So we can't do everything ourselves. And a lot of the time we're working with amazing physicians or even researchers that build models, and they want to use our system to deploy them. And the way we were thinking about it is we really want to enable data-driven medicine. And we feel it's much easier to start with medical imaging analytics and bring the text data on top of it to truly enable to have prediction and statistical analysis. Deep learning is very, very good to bring similar cases. And so do the analysis on them and then keep adding layers. And that's what we're working on at the moment, especially in oncology. So to show you an example of what we've done, this was just over the summer. I think we've done it in 4 weeks. This was brain tumors, a different type of problems about texture analysis. So in the brain, you have to find the core tumor, the enhanced tumor, the whole tumor in volume, and that takes a lot of time. And so here we train the system, and then here you go. This is live. This is on in browser as a video. The system will just basically look at different kind of acquisition and learn live how to do it. Click on lesion, you click on there, you find them, then you can modify them at any time, and all different texture analysis is done. When you show that to doctors, they spend hours today doing it. They truly flip out, and it really opens a field of what can this technology do to change medical imaging and healthcare as a whole, clinically. So thank you very much. It was a pleasure to be there.
Thank you for the invitation. It's really great to be here. My name is Dennis Wall. I'm from Stanford. I'm in pediatrics and biomedical data science. And I'm going to try to talk a little bit about one of the problems we're trying to solve, which is actually something that's already been mentioned a couple times here in this conference. That is a problem represented by autism, which is arguably a deep learning problem at many levels in terms of how these children learn and unlearn various things, in terms of how the behaviors are manifested and how we observe and diagnose and detect autism. We do so actually behaviorally in images, and those images, of course, become amenable to many things that help us improve care and identify symptoms and track progress in ways that we can't do today in the healthcare system. It is a public health challenge. It's a massive epidemic right now. It's been on the rise. Today, it's now an incidence of 1 in 68 children, getting close to basically 2% of kids have a diagnosis of autism. Problem with this is that right now our ability to diagnose is limited in a number of ways, primarily limited by the standard of care, the kinds of instruments that we use and the intake processes that we undergo within hospital systems are too long, require too much time-intensive human-to-human interaction, such that waiting lists are 18 months, potentially even longer. So children are actually not getting diagnosed until after windows of developmental plasticity, where behavioral intervention can have its biggest impact. What's funny about it is that when we observe autism in the form of its behavioral manifestations indicated here in these home videos, most clinical doctors who do diagnostics on children with autism can recognize almost automatically the signs and symptoms within even video clips like this. Some doctors will say that when they walk from their office through the waiting room onto the clinical room, they can actually hear autism as they walk through the waiting room. So so they have the instincts, they have the ability to make these detections far faster than they're doing today. They're not doing it. There are a few kids on the screen here who do have autism, and all the clinicians that I've worked with who do diagnostics I pick them up very immediately. So what I've been working on is a mechanism to apply machine learning and increasingly deep learning. I'll talk about aspects of where we're using deep learning specifically to create a quantitative system so that doctors can act on that intuition automatically in the time frame of minutes as opposed to the many hours that it takes today to do diagnostics. Why we do this is because we want to be able to identify where these kids are and what they need, and some of the things that we're doing in my lab is focused on this, identifying gaps. There are huge gaps in access to resources. These gaps are growing and growing and growing, and so it becomes an incredibly pressing need to develop diagnostics and therapeutic intervention systems that can mobilize, that can go to the homes of the families, that can complement care and obviate the need in certain circumstances for clinicians to act directly with those individuals. So you can have continuity of the learning processes that these children must undergo to enable the synaptic pruning that neurotypically developing kids have when they're undergoing their own brain development. And mobile, of course, and there's no reason I should say this to you guys, happening a lot. So what we've been able to do is to develop a machine learning-based system that has fundamental standard machine learning components in it, as well as deep learning components in it, to simultaneously capture video of children from home, short home videos, and work on those videos with a process that represents essentially human-in-the-loop domain adaptation, which is a part of machine learning wherein you take unsupervised approaches to noisily label lots of data and then have human experts come in and correctly label a few frames and leverage those new manually labeled components to increase the classification accuracy of the base model. This is a critical part, I think, of the opportunities for deep learning or machine learning and deep learning in healthcare. Labeled data is a challenge. How are we going to get sufficient amounts of labeled information that can enable us to build robust classifiers that work on increasingly complex symptoms like autism? Right now, our machine learning approaches have enabled us to target the most highly ranked features, and there are very few of them. They can be observed in videos that are 1 to 2 minutes in length. There are about 15 features in total, and we can leverage this process to not only do the diagnostics in a mobile platform, but to also get labeled data that we can leverage for future machine learning development efforts. One of the things that the field has lacked to date, the field of even developmental pediatrics and child psychiatry is quantitative scores that can be used to objectively measure the presence or absence of a particular condition, not just once at the time of diagnostics, but multiple times during the course of therapeutic intervention. And that's exactly where these kinds of machine learning approaches can come in and make an impact, and that's exactly what we've been trying to do. So we can detect remotely. So we've actually mobilized this into platforms, apps, basically that parents can download, upload videos to those apps, and we then immediately create this data feedback loop on which we operate, right? So we get the data, we can label the data, we can run the first machine learning algorithm on it, we can get manually labeled experts to label some components of that, increase the base classification accuracy over time, and we've done this a lot. In this case, it's dropping off the screen, but it's 10,000 tests so far, 94% accuracy against the best estimate clinical diagnosis, taking minutes as opposed to hours. So an incredible improvement over the standard of care. It's not just happening, it's not just comparing this process in terms of its speed to the clinical speed. It's happening outside of the clinic, way upstream of the clinical visit, so that you can actually leverage this kind of approach to break open the bottlenecks, to triage kids off the waiting list. If they're diagnosable in the waiting room as you walk through it to your clinical office, they should be diagnosed in minutes, not hours. And so we think that this is an opportunity to crunch this clinical standard of care down by a lot, not as much as that slide showing, but 90 to 99% is what we've been able to estimate. And this, of course, has all sorts of reverberations through the healthcare ecosystem costs and things like that that are really positive. And another thing that this, of course, enables us to do is once we have this quantitative score, we can track progress, we can plot kids like mine, we can observe responders and non-responders, a lot of things that are extremely valuable to the care of the children, the perpetual care of the children, but also really valuable to the development of future methods that are based on these data. Some of this is in a company, and we'll talk about it. But I do want to talk about an important part that, again, was also mentioned even today, is we know that there is a hope for reversing signs and symptoms of autism, but it's only a hope if it's done during developmental windows of brain plasticity where the behavioral therapy can have the biggest impact. And so we're trying to focus in on that by building a mechanism that's grounded in machine learning to detect kids early, but once we detect them, what do we do with them? There's so many kids out there, and the clinical, the number of clinicians are far outnumbered by the number of kids who need the care, and the care is intensive. It's person to person. It's behavioral training. It's behavioral training that's actually done using flashcards just like these, where they have to teach the kids, reinforcing them, not to learn the wrong sound for the animal, but to actually understand the face of the person that they're interacting with. What is that face emoting? What is that face saying to them? They have to first learn to look to the face, then they have to understand what that face is saying. This is their fundamental deficit, one of them anyways, one that the behavioral intervention programs work on most aggressively. And it's an image analysis problem, and it's one that we've converted into a true deep learning problem. We can extract this non-scalable flashcard-based therapy out of the clinical operation and put it into a wearable device represented by, in this case, the augmented reality form factor of Google Glass to provide peripheral cues to children in real time that not only help them to look more to faces, but that actually teach them what those faces are exhibiting emotionally. And this is something that we are doing using deep learning, where we're extracting image data from the camera, the forward-facing camera of the glass units, and working on those in real time using a base classifier that's been trained on lots and lots of manually labeled facial image data. But it's also a data feedback loop. And so by the way, this is sort of what happens. This is what the kid sees in the glass if they want words, but there can be emoticons and many other kinds of feedback mechanisms that are provided. This is tethered to a phone, which does all the operations, and that phone actually contains the fundamentals of the machine learning system that we've developed, which works on the images to provide simultaneous face tracking and emotion recognition through a convolutional neural net. And we've been able to get it to go at a speed that's real time, that's dynamic, that's providing feedback immediately. This not only does that feedback, but it also captures data as it's going. So it's capturing the faces of the people with whom the child is interacting, the child's wearing the glasses, and it's also recording social video. coupling this with our mobile diagnostics, we have a two-pronged solution. We have a way not only to teach kids therapy, teach kids how to understand faces and administer wearable therapy, but we can watch how they're doing through our diagnostic system to quantitatively track their progress over time. So this creates this data feedback loop that I've already talked about, wherein the thing that we're delivering as a clinical solution provides a therapeutic intervention while simultaneously capturing data that we can work on to continue to personalize the approach and make it as precise as possible for the family, for the child, et cetera. And that's it. I think I'm out of time. When did that go to 0? Very. There's some, right, so obviously this is what I just said. We're trying to combine these things in a complete solution for use at home as a true application of machine learning and increasingly deep learning for healthcare and providing this continuity data feedback loop that I talked about. And I think that's it. I'll stop, sorry.
All right, bringing up the rear here. Almost done. All right. So one of the things I'm going to talk about is I think something a little bit different. I want to step back. You know, a lot of the conversations about AI or deep learning in healthcare is I've got this one, task that maybe doctors are doing now, and how can we do it, way better, faster, bigger, more accurate, reduce variability with machine learning, deep learning. But I'll also suggest that another area where we need to apply AI, deep learning, is to step way, way back and sort of rethink some of the assumptions we have when we apply artificial intelligence to medicine. And I'll get to some specifics on that. Looks like my fonts got replaced, but they're working. And I have to orient you a bit on how we think about, or how I'm thinking about this, and that is by appreciating that there are rarely smoking guns in human health, right? There's rarely the magic drug, the magic gene, the magic biomarker that's going to be the solution to all your problems when you're trying to diagnose and treat, et cetera. For the most part, what we're looking for in health is smoking gun chips. I'll give you an example just in the genetics world. Inflammatory bowel disease, Crohn's ulcerative colitis, genome-wide association studies have now found over 200 genes associated with those disease, genomic loci. Those don't even explain yet 50% of the genetic component or the heritability of that disease. So when things are all said and done, when all the genetic tests that we need to do on Crohn's and ulcerative colitis are done, we're going to have something like 400 or 500 genes underlying that disease, right? So where's the drug target or biomarker in that mess? And this is actually, for most complex diseases, the norm, right? And this is not surprising, because if we step way, way back and think about the body, right? Complex dynamic networks underlie all aspects of the human physiology and health, right? If we think of just one cell in the body for a second, we have billions of variables in the DNA, which express thousands and thousands of mRNAs and microRNAs that create their own sort of network, which make proteins, which create a whole other layer of network, thousands of them binding back to the DNA. The networks interact with one another. They create metabolites, et cetera. We're still inside one cell yet, right? So billions of interactions, millions to billions of interactions, whole constellation of things whirling around in a single cell. Cells form tissues. Cells communicate with one another. That's another layer of networks, right? And then they form organs. Organs communicate with each other, right? And of course, if everything in that box was all we had to worry about, life would be good. But the environment interacts with that. It's another layer of networks, the gene by environment interaction. So there's layers upon layers upon layers of networks, right, is what's we have in biology. And of course, in other things we've been looking at today, we've been seeing layers upon layers upon layers of neural networks, right? So again, we're seeing these parallels. But one thing we have to appreciate is that humans are complex adaptive systems. This is the point. And complex adaptive systems are a well understood thing or phenomenon in math or statistics, et cetera, and they have specific characteristics. They evolve over time. They interact with one another. The whole is always greater than the sum of the parts. You cannot understand the whole system by looking at its parts, but what do we do in biology and medicine? We try to break the whole system down into its little tiny parts and study it one part at a time, but we know you can't do that with complex adaptive systems. That doesn't work. By the way, who said this? It was an investment banker in Harvard Business Review. So as much grief as we give the bankers, they have a pretty good understanding of complexity. So one of the things I'm enamored with is this concept of, we have this taxonomy or a landscape of disease that is quite antiquated, right? So diseases, the hospitals today, organized still by symptoms and anatomy, right? Symptoms, this happens to a heart, so it's a heart disease. But what we're showing in this very old paper from when I was, in fact, a student a long time ago, is if you actually take, in this case, molecular data, the genomic data, we took genomic data on hundreds of different diseases and looked at their gene expression patterns, basically looking at molecular patterns of the disease. And we start to relate diseases to one another at the molecular level. the sort of symptoms and anatomy-based taxonomy doesn't hold up at the molecular level, right? So for example, Alzheimer's disease looks a heck of a lot like actinic keratosis at the molecular level. Skin disease and a brain disease seems totally bizarre. By the way, there's another group that's now investigating skin as a biomarker for Alzheimer's because they can see tau pathology in the skin of Alzheimer's disease patients as a potential biomarker, right? So one of the problems we have is that we have these assumptions about diseases, how they're organized and how they relate to one another, and they're probably mostly wrong, right? So while we're trying to build these models to predict these diseases and these disease states, we have to go back and also realize that our definitions of diseases are also probably wrong, or at least overly simplified, right? So that was at sort of a disease level, a way of looking at this, but we can also do this at a patient level. So at Mount Sinai, we have a nice resource called the Mount Sinai BioMe Biobank. So about 30,000 of our patients, we have full electronic health record data, and we have genomic data on them. They're also consented for recontact, so we're going to start filling in some of these other gaps. But we have genomic data and electronic health record data. And one of the things we did in a paper we published last year, which I think was a very straightforward thing, but was taking that sort of same idea of the disease, data-driven disease connections and doing this at the patient level. So what you're looking at here is for 30,000 patients in our biobank. So the X and Y don't mean anything. The dots are actually individual people. And what we did is we said, well, let's ignore whatever ICD-9 code or whatever diagnosis code's in the patient's record, and let's take all of their so-called objective clinical data, CBCs, metabolic panels, height, weight, ethnicity, et cetera, and let's just represent each patient by those 400 or so different objective clinical features, and let's ignore the ICD-9 codes and all that other stuff. And let's just see, how does the data organize the patient space, right? This is sort of like baby steps towards a learning healthcare system, or creating sort of a Google Maps of our patient population. So each patients are related to one another if they have a similarity across this high-dimensional clinical phenotype space, right? And it organizes into two groups. That's not South America. That's not a big fish. It has nothing geographic. Like the brain can see teddy bears in the clouds. But the point being, the question, if you're a new patient, would be, like, where's my little blue Google Maps dot blinking? And does it matter, right, if I'm a new patient and I would come into this space? And again, whatever diagnosis we think they have doesn't play into the topology here. It's just their raw data. So there's two groups. Just for sake of time, I can tell you don't want to be on that little island over there. I call that cardiometabolic island. It's a bad place to be. But then what we did in this particular case is we then highlighted the patients that have type 2 diabetes. They're one of the most prevalent. So we took the classic definition of type 2 diabetes, HbA1c levels, given a drug of XYZ, et cetera. And we said, where are the patients that have the classic definition of type 2 diabetes? And basically, you see all these little type 2 diabetes hotspots emerge. They're not all in one spot. Long story short, if you take just the diabetic patients alone here, you get actually, and just look at it in a data-driven way, you get 3 separate subtypes of diabetes patients. Who cares? You can cluster data all day long, gets pretty pictures, doesn't mean anything clinically, and of course it would have been published if it did. But I can tell you briefly, because I'm running out of time, so these are all type 2 diabetic patients, broken into 3 clusters. The patients at the top cluster have increased risk of heart attack and stroke and other cardiovascular events. So all type 2 diabetes patients have increased risk of these sort of comorbid events, but that group, even relative to the other type 2 diabetics, has increased risk. The bottom group has increased risk of cancer. Even though all type 2 diabetes patients have increased risk of cancer, that group had increased risk above and beyond the other diabetics. So the provocative idea was, do we have type 2, type 3, and type 4 diabetes patients right under our nose without ever knowing it, because we never looked at our patients in a data-driven way, right? And I can tell you we had genetics on these patients, full genomes, genotypes, and the genetics was not used to inform the clustering. But after the fact, we looked at genetic association with these groups, and why this paper was interesting was, for example, the top group that had increased risk of cardiovascular events. If you look at the genetic variants that uniquely associate with that group, they cluster in things like vascular endothelial signaling pathways and all heart-related things, right? So, and that genetics was not used to inform the topology. So, so we've also taken this a little bit further. That was just using the sort of high-level, messy EHR data that we have and making these big vectors and sort of clustering them and seeing, well, how does it organize the patient space. But even though EHR data you might not think is sort of this really powerful high-dimensional data that you could maybe do some deep feature learning on, we thought, well, let's see how it performs. And in this case, we had a paper come out recently where we took all of the electronic health record data in our database for our patients, and we just put it in essentially a stacks of denoising autoencoders to create a deep neural network representation of our electronic health record data. So a classic thing you might want to do if you're trying to do predictive analytics with electronic health record data, say you want to say which patients go from type 2 diabetes to chronic kidney disease of some type, right? So what are you going to do in that case? Oh, well, we're going to meet with, let's get some endocrinologists together. Let's try to find some patients that did progress and didn't progress and age match them, et cetera. And then we're going to ask the endocrinologist, what are the features you think might be important, you know, for progressing from, you know, diabetes to chronic kidney disease. And then maybe you'll do some feature selection on that, build a linear model, and hopefully that it performs well, right? Well, if you're really, so that's sort of the old school way of doing things. If you're really ambitious, you might say, well, let's just try to use all the features in the EHR and use Lasso or ElasticNet or something like that. But there's probably lots of latent factors connecting across, for example, blood counts and other things that might be below the surface of these sort of high-level features, and that's sort of the idea here, is if we put this in a sort of a deep network representation, does it capture latent features that are important? So long story short, we actually created a deep neural network deep feature and representation of our patients, and then we learned supervised models from those deep features, which was, for any given disease, for example, can we predict new diagnosis of diabetes, attention deficit disorder, cancer, et cetera, in the next 1 year? And what you can see is that the deep patient representation performs quite a bit better for predicting something like 80 or 90 new diagnosis of disease compared to even principal components, general Gaussian mixture models, k-means, et cetera. Very straightforward, but just showing that this representation works quite a bit better and captures information that just the raw EHR data doesn't capture. And in fact, we also think that this will build models that are more portable across EHR systems is something that we're looking at. So the one, I guess I'm out of time. I got to finish really quick. But since everybody else went over by a minute, I want to give you the, everybody talked about sensors. This is boring. You all heard this today. But the one point I want to make, we've got an asthma app and health kit. We're doing all that crap. Everybody's doing it. But the point I want to make is there's been a lot of talk about wouldn't it be great to catch, I can't go backwards, longitudinal dynamic data from apps, and can we do molecular profiling, genomics, microbiome over time, et cetera. But why do we need to do that? Why do we need that dynamic data? I want to make a point is, we want to understand the genomics. Genomics is somewhat of a disappointment in terms of clinical applications right now outside of pharmacogenomics and et cetera. The clinical utility is somewhat limited, but there's a reason for that. It's because we have very limited phenotypic information. So I'm going to give, I have 1 minute left, so here I'll give you a whole genetics lesson. This is a good idea. What we're looking for often in genomics is functional relationships between DNA and other things. So for example, we look for expression quantitative trait locus. Sounds really complex, it's very simple. We're looking for correlations between genetic markers and expression levels of some genes, because that might tell us that there's a relationship between the function of that part of the DNA and a particular gene. Here's a very classic example of an eQTL. What you're seeing here is a particular one position of the genome, a SNP, and you're seeing a classic expression quantitative trait locus relationship. So basically, each dot is an individual. Everyone who has 2 copies of AAA has higher levels of expression of HIP1 on average. Each one with GG has lower expression levels of HIP1 on average. And the people with a copy of G or A, the heterozygotes, have medium expression. You could swap out the expression levels of this gene for height, people who are taller or shorter, or something like that, right? But what they showed in this paper is that if you stimulate these cells with a pro-inflammatory agent, actually the functional relationship actually flips around the exact opposite. So 2 hours after pro-inflammatory stimulation, that functional relationship goes away. And 24 hours after pro-inflammatory stimulation, it's the exact opposite direction. So someone could publish a paper that says, this SNP is associated with high levels of expression of this gene if you have that genotype. But actually, if you look at it 24 hours later after pro-inflammatory stimulation, it's the exact opposite direction. The whole point of this is that the function of the genome is highly, highly dynamic, and it changes based on the context of the environment and time. It can change minute by minute. But we don't have all this information. We can't just put people in a box and throw a bunch of chemicals at them and challenge their physiology in a way, right? To learn all these possible relationships, right? So what we need is to build these, deeper integrated data sets and then apply deep learning so that we can learn a lot of these potential relationships about how the genome works, even if we haven't explicitly measured these on cells or on individuals. And what I hope we move towards is what was articulated by Eric Topol, which is a geographic information system for a human being, where we have many layers of information. and we're guiding someone's health course in real time, right? We've built up a data set that helps people sort of navigate the optimal healthy peaks and stay out of the disease valleys in real time, right? So we can sort of navigate across an optimal path of health, right? And I think this is a goal of a lot of other people here, but the critical piece is we're missing a lot of this deep phenotypic data that will help us build these models. And that's something we really need to build up. Really apologize for going over my time, but thanks for listening.